What about now? It's
Great,
on. Oh,
great.
okay.
Thank you.
Okay. Good afternoon and good morning, everyone. Depends on wherever you are. Today, I will try just give you some overviews to walk you through some of the interesting concept behind this causal inference. First, I will go try to recap what we have discussed last time, and then just add some of the key concepts that I missed from my last presentation, because they are very, very important, especially if you are really you want to join this causal evolution or causal inference uh, group. And then we'll walk you, just briefly tell you about what is this structural causal model, what it entails, and then some of the tools that can be used within this structural causal model or within causal inference. There's some interesting method called do calculus. This thing is very vast and very, very wide, and I really may not go to the detail, but if you are really interested to join this field, I really just encourage you to dive into the science of these techniques. And then I will discuss a bit on how to estimate causal effect using observational data. Here also, I may not really go to the details of details of these estimation techniques. I may not also discuss all methods, but just I brought you very, very interesting topics here, and then you can also go dive into this topic. And then, for the remaining topics, I really recommend you to read. And finally, if we get some time, because today is the last day of our capacity building session, I want to hear from you about what went right and what went wrong on our approach to this capacity building over the last 5 or approximately almost 6 months. So just to give you some recap, remember, we defined causal inference as it's a process of determining the relationship between cause and effect. And also we defined as causal inference as a use of observed data to infer causal relationship between two variables based on known or hypothesized mechanism or model. Or we may define causal inference as is about discovering the causal structure from the data. But data is not enough, if you remember our last time discussion. Beyond data, we have to go back to the external body of knowledge just to understand the data generating mechanisms. We cannot really infer causation only from data unless we go to the external knowledge about the body of the systems we are really investigating. And therefore, it requires some identification and estimation strategies of some counterfactual world, which we cannot easily learn from the existing data alone. Sometimes even when we have some intervention or some action, like we may not really necessarily get, every intervention cannot necessarily really imply causation, because the relationship between those two dynamics or two variables can be also affected by other confounding variables. So we have to, this implies that, our knowledge about the body or the two systems or the variable of interest we're studying, external knowledge about those systems are really, really critical before we rush into causation or we rush into causality. I also just brought these graphs. This is Peirce hierarchical or so-called the hierarchy of causation. Like, if you want to understand what is happening around us, we may start from association. We always observe, we see. what we observe may not really imply causation, because there are some regular pattern around us that always happen together. That those two events may be correlated, but they does not really reflect a causation. For example, if you want to know what does the systems tell me about the disease, or what, questions like observational questions like, what if I see X variable? Uh, if I how would I seeing X change my belief on Y? How are these two variables, how are these two phenomena of event can be related? That is called association. But beyond association, we may be interested to predict the effect of some interventions by deliberately providing or giving some action so that we can maintain or get some causal relationship. And the third hierarchy, the most important and fascinating hierarchy, is about this counterfactual world or counterfactual thinking. This counterfactual world is about imagination, about thinking retrospectively, about understanding the phenomena of interest. It involves construction of our theory about the world or about the phenomena of interest that we're going to explore. And then ask ourselves, like, what would have happened had, or what would have happened had this kind of, imagine what's happening in Kenya, for example. Like asking, if you are thinking like as a counterfactual thinker, is like, what would have happened if this bill or the financial bill has not been ratified or has not been issued? Do we really observe this ongoing unrest or ongoing civil disturbance? That is a counter that asking about what would have happened really. Is this the financial bill is the real cause of this, the ongoing civil disturbance? That's called counterfactual thinking or counterfactual understanding or imaginating about the phenomena of interest. So imagine we have some questions like, what is the effect of drug or intervention? Like, for example, in the case of mental health, we want to estimate like the effect of group counseling on reduction of depression or reducing depression, or the effect of some drug on reducing depression. So the best approach is like, seeing me taking the drug or receiving those interventions at two time place, like seeing my depression status when I receive the treatment, when I receive the drug, also seeing my depression status without receiving that treatment. But that could not be happening. It's difficult for me to be in two states at the same time. Once, if I receive the drug, I receive the drug. The only potential outcome that I observe is either my depression reduced or not. Or if I don't receive that drug or intervention, the potential outcome of my depression could be reduced with some other factor, or it may not. I don't know. That is a counterfactual world. But it is difficult for me individually to go back in time, unless I have some time machine or time travel machine that takes me back and see the phenomena, what would have happened if I had received or had not received the treatment. That is very difficult. Therefore, the way we want to estimate this, we want to find some comparable or comparison group, or someone who is really similar to my characteristics, or some units or some individual who have the same characteristics with me. Like if I receive that treatment, I consider the other guy or someone who has the same characteristics with me, like age, gender, and other factors, unless all factors which we have similar characteristics. The only difference between both of us should be the treatment, having the drug or not, having the intervention or not, and then see the average treatment effect between I receiving the treatment or the drug minus the average treatment effect of the someone or the guy who is comparable with me without taking the drug. That would give us some the average treatment effect of the effect of the treatment. So to answer that question, okay, if my question is what is the effect of the drug on depression or the effect of group counseling on depression, the best way to answer is, as I said last time, is to conduct randomized control trial. Because why randomized control is the best option? Because it's randomly assign an individual to receive the treatment and on control. It's the only reason why I receive the treatment is because of chance. It's because, for example, if I toss coin, that is the main reason why I receive the drug without any confounding factors. The main reason why I'm assigned to the treatment is because of tossing the coin. That is a chance. Therefore, there is no other factors that I would really can imagine that the relationship can be confounded when I try to compare the effect of compare depression between those who received the drug as compared to those who do not. Why randomized controlled trial is usually considered as a gold standard, or sometimes they call it as an ideal weapon for estimating causal inference or to understand causation is randomized controlled trial. But I remember there is some caveat. RCT may not really give us causation. Doing RCT by its own doesn't really necessarily give us a causation. But compared to the other study design, randomized controlled trial is the best option. Okay, why? It randomly assigned, it balances coverage, it avoids selection bias as compared to observational studies. Imagine if I do not assign my treatment randomly, and if I allow someone to receive some of the intervention, sometimes people may self-select themselves to join the program, for example. Imagine if you want to compare the effect of like safety net program or the effect of like giving money, like how like there is some intervention in Kenya, for example, they give money to some population and then see how people can spend their money without doing any work. It's called give directly. You can read about the studies. They give directly the money during the time of COVID to some of the populations. Look, people are very much attracted to this money. So when the community heard about this intervention, more likely people are really self-selecting, voluntarily go to this program and receive the money. Therefore, probably at the end of the day, if we want to compare the effect of that giving the money on spending or on expenditure after some time, we may compare some population who are really not comparable because there is some self-selection bias. There are some voluntary population or voluntary community who really went to receive that money, but they have some special characteristics or different special characteristics as compared to those who do not receive that money. Therefore, they are prone to selection bias. The other important advantage of this RCT is about it has temporality dimension. It controls the temporal effect. That means the intervention always precedes the outcome. But RCTs may not be really applicable or practical because of cost. It is really resource intensive. Because of ethics, it is difficult to conduct some of the RCT because of ethics. For example, if you want to estimate the effect of smoking, like during pregnancy on birth outcome, it's really unethical to like randomly assign pregnant women to smoke or not to smoke. That is really unethical because we know that smoking has an effect on lung disease or lung cancer. So sometimes because of time, we don't have time. We may not get enough time to really randomly assign population and do some intervention and then follow for some time and see the effect of the intervention after some times because some of the project, for example, is run out of time. In terms of practicality, some of the intervention could also be very, very difficult to manage, to design like randomized control trial. Therefore, in that case, in that scenario, we rely on observational or quasi-experimental studies. We are really opted to choose observational data. So the big issue is now, how do we get an equivalent estimate by using observational data as had we conducted randomized control trial? So how can we really get the same estimate, estimate if we use cross-sectional data, if we use observational data, if we use cohort data or case control data or longitudinal data? These are all categories of observational data, so that we can really estimate get the same estimate as a randomized control trial. One of the main challenges that limits or prohibits observational data not to get the same estimate as an RCT is because they are really prone to confounders. We have a lot of confounders are really operating between the variable of interest, the phenomena of interest we are really interested. The issue of selection bias is very common in observational studies. We don't know the counterfactual worded again, okay? So that is the main limitation of observational studies. So I also raised two important frameworks of how do we really understand the systems we are really trying to explore. One is about using the potential outcome framework. Like within that counterfactual framework, I said, we compare the potential outcome of a group who received the treatment as compared to the potential outcome of those who do not receive the treatment. That gives us the true causal effect of the relationship between two variables. The other framework I also raised is about, the utilities of this DAG. I said this DAG is about representing our reality, our model of the phenomena of interest we want to explore. DAG is a collection of variables or nodes, like mathematically they call it nodes or dots, representing variables, and then directed by edges, or this edge connects the nodes. For example, when this variable labeled as X, Z, Y, W, these are all nodes, or for us, like think in terms of the variable of interest we really want to explore. X could be our drug or intervention, and Z could be the mediating factor in between the two. And Y would be the outcome of interest. That's reduction in depression, for example. But between X and Z, there are two things happening in this graph, for example. W is the pathway between X and Z. That is a mechanism. That is a path between X first cause W, W cause Z. Could happen. But the other important feature is about U. U is an observed phenomenon that could affect both X and Y. It happened. Why U? You usually, especially in observational data, we tend to forget to collect very critical, important variable. There could be some unmeasured variable in our actual data that can be represented as a broken line, and the U is an observed or unmeasured confounder or unmeasured variable. So when we use DAG, I said, always remember three causal structure, three possible causal structure. Whenever you draw your DAG, remember three things. One is the mechanism, or the so-called causal pathway. The path from X to Y is through M. If M is a full mediator, imagine X only cause Y through M. We are saying like that. Sometimes M could be a partial mediator, but if M is a complete pathway between X and the Y, M is our mediator. But sometimes there are some confounding paths, okay? That these confounders cause both X and Y. X and Y are naturally, they are not related, but because of C, they could be related. Therefore, these confounders are the main reasons that connect X and the Y, but they are independent, okay? You know, we should really get mistaken, like associating X and the Y without getting or without really looking into C. If we are always observing two phenomena I raised, remember, something really, some regular pattern, always happening again and again, always happening again and again. That, like, you know, for our brain, seems like that these two phenomena can be causally related. Next, I raised the issue of crowing the rooster. When the rooster crows in the morning, after the rooster crows, the sunrise. That is something that daily happen in our life. So if you put it like in our model, definitely you will get some correlation between the crows of the rooster and the sunrise. But can we really associate? Can we really say that a crowing of this rooster is the main cause for the sun to rise? Not, because we don't know. There's some confounders. There's some variables that which really we don't understand, which affect both the crow, the rooster to crow, let the rooster to crow, and at the same time that let the sun to rise. That could be unobserved. We could also observe. Therefore, similarly, you can take the same analogous or the same analogy, like when you want to understand the relation between the variable of interest in your model, especially when you write your protocol, think about what possible confounding factors could really be available or could happen between the two variables of interest. The other most important, but often neglected causal structure is this collider path. Two variables can collide and falsely associate, okay? You know, like kind of, remember, I also use some jargons of word like parent and the children. Within this causal structure, you will get some words like the parent, children, ancestor, descendant. This kind of terminology was there. You can refer the first lecture. For example, two parents can have a child without marriage. That is Z. Z is a child. But doesn't mean that whenever you see that, the child, you may falsely associate that two parents are really married. Like X is for example, the man, and if the Y is the woman, and Z is a child, you know, okay. Whenever always you see that child, you may falsely, you know, your brain falsely associate that, you know, these two couples are really married. But in actual case, they are not married, but they have children without wedlock. Okay. Therefore, observing that child may let your brain to associate, you know, to think like, okay, these couples are really married. So same phenomena could happen in our body of systems that we want to understand. Okay, if you look at the D, the final graph, that is when we have a combination of the whole. Actually, it could be more than this. I have showed you, I've shown you to some of these graphs. It's a complex graph we have. Like we may have this structure as complex as it is, as containing the three causal structure. Contain colliders, contain confounders, contain mediators. Could be some risk factors only associated with Y. It could be some factors only affecting X. You know, there are some factors affecting C. Could be more complex than this. But whenever you look at, just try to understand in your graph whether you have a collider, you have a confounder, you have mediator. Why? Because they are very critical for you when you do some estimation, like when you model, for which variables you are really supposed to adjust. Okay, should you really take into account when you model. Within that, I forgot to mention about this fork, this confounding, or sometimes you will get, or definitely you'll get when you read literature on this about deconnected. Okay, there are two passes from X to Y. How X could affect Y in this graph, actually it is three. One, X cause Y, that's the direct causal path. Okay, X cause Y through Z. Okay, through backdoor. Z is a backdoor for X to cause Y. That's called backdoor. But X can also be related to Y through an observed variable, actually. But in case if we assume that, one of the assumption of observational data is no unmeasured confounders. That means we have already collected all variables that should be in our model just to represent our reality. Assumption we have from observational data to estimate causality is about no unmeasured confounders. Suppose we don't have this Y, okay? That means the path between X and the Y is through either directly through Y, directly from X to Y, or through indirectly through Z. Like X through Z cause X, Z cause Y, so X can be related to Y. So when X connects both X and the Y, we could say X is deconnected, That means in reality, these two variables are not connected, but the presence of X could connect X and the Y. That is called confounders, or especially if you are in a machine learning group or the science of that machine learning, you may see the word fork, like the acts like fork. So we need to close this. Okay, if you want to model, remember when you draw your DAG in that DAGITI, one of the things always, the first thing that always that tool did or do is about closing the doors. That means adjusting for that. How do we adjust? We may estimate some propensity score, or we may stratify some of our model, like stratification could be one of the way we can adjust. We may use some regression, like adjusting for that may solve. But there are some limitations when you use regression. So, okay, when we adjust for that, it's called deseparation. We're separating between X and the Y because we have adjusted for Z. So the conditional independence between X and the Y given Z holds when we look at two things. One, we have to identify all paths from X to Y. I said it's through X to Y directly or X to Y through Z. And then we have to check whether if this path is blocked. The path is blocked if at least fulfill the following conditions. One, if it includes no collider vertices that is in Z, that means Z should not be a collider. If it includes a collider, that is not in Z and no descendant of any collider of Z. That in that case, we could say the path is blocked so that we can isolate, or we can say we can identify. So that fulfill a backdoor criterion, or it should be adjusted for our model when it fulfills two criteria. Just about repetition of the first slide. If we want to identify the causal effect of X on Y given Z fulfill a backdoor criterion if the following assumption holds. One, if there is no vertex, that's a line that descend from X to Z. That means when we always model, even in randomized control trial, don't put any variable which occur post-intervention. One of the limitations that we always commit, one of the mistakes that we always commit is we always adjust some of the variable for post-treatment, after some of the things that happen after we intervened. Okay? That means, but the assumption for backdoor criteria is we shouldn't have any descendant of X. Okay? The second is Z should block all paths between X and the Y with an incoming arrow into X. That means we should adjust for that. In that case, if we do that, our estimation is a summation of the product of, or the distribution of the outcome Y given X is set to X and Z is set to Z. And because Z, there is no incoming row to X, so the probability distribution of Z is the probability of Z by itself. Therefore, when we multiply this condition, like remember the joint distribution, or remember about the multiplication probability, multiplication ruling probability and addition ruling probability, is a summation of the, for each value. This we are saying that for each value of Z, for each distribution of Z, we multiply the value of Y given X given Z by the product of, by the probability of Z. So remember this first graph. Okay, sometimes we may have such kind of complex graph, like for treatment, you know, our variable of interest is we want to estimate the effect of T on Y. But our DAG, the causal diagram from observational data looks like this. T can cause M through, and then M cause Y, or C is the main cause for T and the Y, that is confounder, this is mediator. Or sometimes there are some variable cause T, and that variable has also another grandparent, W2, and this grandparent can cause another variable, so-called W3, and W3 cause Y. So if you look at the causal path, you know, remember whether we can fulfill this backdoor criteria, which variables can fulfill the backdoor criteria. We have to think two things. One is, what is the pathway between T and the Y? One is through M, that is called causal path or direct path. The other is T can be associated with Y through C, that is through confounder. C is a confounder that is responsible for the cause. But again, T can be associated with W through W1, W2, W3, and the Y. There are another paths that really should be blocked. Okay? So if we want to estimate the true causal effect of T having this graph, we have to really adjust for C and W2. Okay, why? Why W2? I think C is very obvious. Remember, if you look at the relationship between W and W3, when we have W2, we associate W1 and W3. Okay? If we associate W1 and W3, the path from T goes from W1, W3, W, and Y, unless we adjust for W. Which I said, whenever we have such kind of forks, like W2, that is a confounder. Confounder always should be adjusted in our model, okay? Whenever you look at any graph, DAG, make sure that you have really correctly identified colliders, confounders, and the mediators. But the most dangerous bias is mostly happening because of confounding and also because of the collider. Okay, so when we don't adjust for W, we falsely associate W1 and W3. So the path between T and W3 and the Y will open. But we said we should be closed. The door should be closed to estimate the true effect of T on Y. Therefore, adjusting for W is very, very important. Okay? Oh, this is from the observational data. But sometimes, if we conduct a randomized control trial, RCTs, that means the assumption, remember the assumption behind RCT is about there is no confounding affect both groups. They are balanced for both groups. Therefore, the only reason someone would receive T, the treatment, is through chance. Therefore, we don't expect incoming arrows from 2T, from any variables, if it is good RCTs, okay? Unless we do some bias, if it is randomized trial, someone will get treatment only through random assignment, either through lottery or through some computer generating mechanism, whatever the case. Therefore, we don't expect any incoming rows incoming line from C to T, from W1 T, because we intervene. We said do T. Do T means if we intervene on T, our graph would look like this. Okay, let's look at this graph. How can we identify the causal effect of T on Y? Okay, imagine you get this graph. The first step, I said, is remember the three causal structure. Okay, from T to Y, T can be linked to Y through different paths, at least three different paths. One, T affected by Z and Z cause Y. That is confounder. Remember, this graph is fork. Or T through Z, through U, through X, and then Y. That's another pathway. Or T can be associated with Y through U, through X, and to Y, through this path, this line. But remember, there is some collider here. Colliders, when two variables collide together, this is called collider. X is a collider, right? T is also by itself is a collider between U and the Z, because two rows coming together, okay? And we have also confounders, okay? That is a confounder between T and the Y. So if we want to identify the causal effect of T on Y, first we have to look at the paths and then check which paths should be closed or which paths should be conditioned on. In this graph, I said, don't adjust for collider, okay? If we leave it like this without adjusting for it, don't put X in our model. If we leave it as it is, the door is closed. But sometimes we mistakenly put some of our variable in our model. Collider, when we put collider in our model, we falsely create some association, as I said, child and a parent relationship. Therefore, naturally, just by looking at this graph, naturally, path 2 up and the path 3 is closed because they are X is a collision for multiple variables. Okay, so the only path we should really worry about is path 1. So let's think like, imagine we have this set of variables. So the minimum set of variables that we are really supposed to adjust is only through Z. You may have this is your structure for the systems that you want to understand. You can draw like this, whatever, but you shouldn't really put all variable into your model. So the only variable that's critical for you is Z. So when you condition on Z, when you adjust on Z, you will definitely close the door so that you can estimate the true effect of T on Y. The other path is about front door pass. Most of the time, without let's just complicating, when they say front door passes, just thinking about how do we really take into account some mediators. That is an issue. how do we, we are going to estimate the causal effect. So how do we handle this mediator or Z in this graph? We want to estimate the effect of X on the Y. So should we adjust for Z or not? That is the question. So first, Z satisfy the front top criteria. A variable could satisfy front load criteria if it fulfills the following assumptions or the following criteria. One, Z should completely mediate the effect of X and Y. Okay, I know in reality, sometimes we have some partial mediation. I know some of you have, for example, when you conduct structural equation modeling, you may get some partial mediation or so-called indirect paths. But that is not enough to fulfill the front door criteria. If Z completely mediates between X and the Y, that means all causal paths is through Z. So there is no unblocked path from X to Z. Okay. And also all backdoor from Z to X are also, to Y are also closed. Therefore, given the order of pair of variables that we have, X and the Y, just read this assumption. Z could satisfy the front door criteria when it fulfilled, when every directed path from X to Y is intercepted. That means Z is a full mediation, a complete mediation for Z, a mediator. And then there is no backdoor path from X to any of the variable. There should not be any confounding between X and the Z, in other words. And then X blocks every backdoor path from, when you estimate, remember, use causal mediation analysis or a structural equation model. Here is the 3 steps, if you remember. First, you estimate simple structural equation modeling. You do first, you estimate the effect of X on Z. Step 1. Step 2, you estimate the effect of Z on Y. Step 3 is a combination. You combine, you multiply both effects. That is the structural equation model. But Z, if Z satisfy complete mediation, or it really intercept X and the Z, when we model the effect of Z on Y, X should block. We should really adjust for X. That means X should block the backdoor path from Z to Y. Okay, X should be adjusted for. Then when this Z, the mediator fulfills this front door criteria, our average treatment effect or the estimation is a summation of the distribution of for each value of Z, we will multiply the product of probability of Z given X with the probability of Y given X and Z by the probability of X set to prime, like when we just give value for X. So to understand more, like to understand the phenomena of the body of systems or the relationship between variable of interest we have, we may, beyond DAG, we may just also go some level of thinking through structural causal model. That is a conceptual model to understand the causal mechanism of the system. That is, according to this Stanford Encyclopedia, they define structural causal model as a mathematical representation of causal relationship within the system. It facilitates about causal relationship from statistical data to also teach us about epistemology, the knowledge of the causation, about the relation between causation and the probability. Okay, imagine we have this DAG. Remember, this is the graph DAG. So the structural equation for this DAG is we are saying B is a function of A. This is colon and equal sign shows a symmetry relationship. It's difficult to label as B. According to Julia, he always preferred to use this notation or this symbol, colon and equal sign, to show the relationship should be a symmetry. That means, imagine if we use equal sign. B equal A means A can also cause B. But when we write B colon equal, just to, transmit or to tell our reader that we're saying that B is a function of A. But B can also be written like B is a function of A and also caused by an observed U. Therefore, B can be caused by observed or measured A or unobserved U. So when we say structural causal model, it's defined as it's a set of tuple where we have some endogenous variable, okay, in our model. Remember, this A and the B are endogenous, and we have some exogenous, some random or noise variable that is called U. Okay, this is a noise or exogenous variable, and this PU is the joint distribution of, imagine we have this graph, for example. Okay, in this graph, we have only one PU, just one only effect, but we also expect some U for A. There's some exogenous variable that really can influence A. Therefore, this U should be independent. Okay, and then the joint distributing of U is a product of those independent exogenous variable. And F is the function that determine or simulate how the values are assigned. That's a set of functions, the structural formula or equation between these V, X, and the U. Therefore, for each variable assigned to X, X is a product or a function of the parent of X. That when we say the parent is a path that directly cause X, and also function of U, that is an exogenous or latent noise that we did not observe in our body of systems. We may not directly or indirectly measure the exogenous variable. Look at this graph. Imagine we have such structure. Okay, when we have this graph DAG, we are saying that A is causing B, A also causes C, A also causes D. For each exogenous variable, okay, for each endogenous variable, we have some exogenous, something outside the endogenous. It's called exogenous variable that cause the endogenous variable. And then the structural causal model or the function that we write is B is a function of A, directly by A, and also by it is noise or it is exogenous variable. C is caused by, we are saying that C is caused by, is a function by A, B, and an observed variable that we do not know, or the latent variables that can affect C. D is a function of A, function of C. C can also influence D, and also by an observed variable. In this graph, we have 4 sets of tuples. One is endogenous, second is exogenous, the third is, we assume that this noise or random variables are independently and sometimes, in what is called is normally distributed. They are independent and normally distributed. May not be the case in reality. And then the function is this one, is a set of functions that we are looking from this graph model, and as it can be expressed mathematically as like this. Example. Suppose we want to know like whether someone who have COVID are more likely to receive drug or not. can having COVID infection, like imagine if you have question of like, do all people or do those who have acquired the COVID really take drug? What is the relation between being exposed to COVID and receiving the drug? In between the two, CAF is the most, remember the early pandemic year, CAF is the most important determinant. And there are some symptoms that really we consider as a sign of COVID. But we don't know some exogenous variable why we acquire or that individual acquire COVID, okay? Because maybe some immunity that is unobserved, we did not measure, or we don't know why those people who had COVID are really having cough. There could be some exogenous reasons why COVID caused cough, some damage on epithelial, on lung cells, we don't know, or some part of the respiratory systems, we don't know. That's why we assume as unobserved. And then the issue is about to measure if someone exposed to COVID would receive drug or not. Therefore, the structural model or the mathematical expression for this graph can be explained like this. C is a function of U, because according to this graph, we don't know which line really connects. We don't have any line which really influence COVID. The only thing we know is someone get COVID because of unknown. And then the other function is about O is about cough. Cough is a function of having a COVID and also unknown. Someone may also cough without COVID. That's could be labeled as U. And then the possibility, the potential outcome of cough having this function, having this COVID would fall into either of this group. Either they develop cough or not. Same with drug. Therefore, this is the representation, the structural representation of our model of this DAG. So how do we use some of these tools? Like in this structural causal model, how do we use this so-called do calculus? I'm really diving into this literature. It's really keep haunting me about this structural causal model and how do we really use do calculus. I deliberately bring this thing, like, I don't know if some of you are really interested to join this field, and really this do calculus is very important. So let me briefly explain what I really understand. I'm not sure whether I really captured it. Okay. So in this structural model, structural causal model, I remember I said there is a question about, okay, if we don't do randomized control trial, so how do we use observational data and estimate similar or get similar estimate as RCT? Okay, how do we get the average treatment effect that we can get from RCT, can also be replicated, can also be obtained from observational data? How? By manipulating some of the things. So this guy, Julia, brought the issue of do calculus, and it has some set of rules. I will show you some. The do calculus is a set of manipulation. You manipulate. That's the word do. I don't know. So you have seen on some of my slides. You manipulate. That means when you intervene, and then you transform some of the expression. Okay. So, okay. If sometimes sometimes we may transform this do operator to without do. That means, can we get similar estimate without intervention from, when we say without do is without intervention, is about from observational data. That is the hallmark. It is an expression that do not include do operator can be estimated from observational data without experimental trial, because the issue is about, why we invest on RCT. If we can really estimate RCT from observational data. So he developed this interesting approach called do calculus. The basic idea of this calculus is about, like, you have to imagine what would have happened, or if we do something, then you calculate the difference in probability with and without that intervention. Therefore, he brought some set of rules of how to manipulate these probabilities to isolate or to identify that causal effect. So in this do calculus, there's a jargon called do operator. That's a mathematical operator which simulates intervention. It's about simulating this intervention when we have, when we set our intervention X. Imagine X if it's set to be constant. So the probability distribution of Y, whether we intervene X or not, would be the probability of Y. Or the model that we see, whether we intervene X or not, would be the probability of Y. Remember randomized control trial. If we do perfect RCT, this expression is perfectly fits to RCT. And then it led you to question about the notion which says correlation is not causation. Look, if you intervene, X is a variable that you intervene, and you want to see the probability of Y. When you say X is intervene, you are saying that confounders are balanced. There is no unobserved confounders. The only thing that makes difference between the two groups is only the intervention. Therefore, whether we intervene or whether we observe, the probability of Y would be the same if it is the only reason for the cause of Y. Philosophically, that is the way. I repeat again. Therefore, in this situation, this condition, whether we do or we without do, if the probability of Y is the same, why would we go for intervention? Okay? When we assume that, example, we conduct perfect randomized control trial, RCT, remember those assumptions. We said there is no confounding, there is no variable that influence between the two variables. Therefore, the only difference is intervening on X, that is on the giving the treatment would change the outcome. Therefore, if the treatment is the real true cause of Y, whether we intervene or not, the probability distribution of Y would be the same. Therefore, this is where correlation would be causation. Correlation can also be causation when X is the only reason that cause Y. Therefore, whether we intervene on X or not, if we get the same probability from both worlds, we could say correlation would not be causation. On the other way, you can also think about average treatment effect and the average treatment among the treated, ATT and AT. So it could be whether someone has received the intervention or not, as compared to the average treatment effect. The average treatment effect would be equal to the average treatment effect among the treated. Okay, so to understand this do operator, let's have some understanding on some notation, mathematical notation, like to understand the phenomena. This is the original graph. Z, W, X, these are variables, you know, they are an arbitrary variable or our variable of interest, where this is the original graph. If Gx bar, like after today, or when you read Gx bar, X bar is saying all incoming edges or rows directing to X is removed. Okay, we are saying that we set the value of X. That means there is no variable, there is no confounder or covariate that really influence X. That is what it portrays. If you give me these two graphs, here I would say, okay, you are saying there is the main reason for X, and W can also cause X, either Z or W can cause X cause Y. But if I look at this graph, I would definitely understand you are saying that, you said X is the intervention. Therefore, you don't need any variable coming to X because we don't expect any variable would influence Z and influence X. Therefore, we have removed, especially this happens in the case of RSATs or intervention. Okay, similarly, imagine we have this graph, similar graph, but when you look at X, graph of X under bar, we are saying that we are manipulated. Sometimes you will get manipulated or mutilated graph. When the outgoing X, the outgoing edge is removed, is called X and paragraph underline. Okay, when we said X bar, and then this one is X underline bar, is below. We are saying that any incoming outgoing from X is removed. We are saying Y is independent of X in this graph. Okay. So how do we use this do operation in structural causal model? I just to understand, to grasp this, I got very interesting note from this guy. So imagine this is our causal graph. That's original graph. We're saying Y, we have X, we have Z, and the structural function we have is X is a function of exogenous variable, Z is a function of exogenous, some unknown factor, and Y could happen by X or Z, that is or sign, okay? And also Y could happen because of an unobserved Y. So W is, for example, imagine kind of simultaneous equation is happening by this equation, 2Y plus some unobserved. Okay, suppose let's intervene. Let's do Y1. Let's set Y at the value of 1. When we set the value of Y, we said, okay, when we intervene, we said we have to remove, when we intervene, we have to remove all the incoming edges into X. Therefore, all incoming incoming edge to Y would be removed. Therefore, Y is independent of X. We are saying that in the second graph, we are saying Y is independent of X, Y is independent of Z. Therefore, we can estimate the effect of Y on W. Okay, so when we set Y to 1, that is the value of W is about 2 plus unobserved phenomena or exogenous variable. Okay, let's take some analogy from fire and smoke. Consider we have some two binary variables called fire and smoke. That is what is happening around us. So these variables, we always look at some point in our home or some place we look at both fire and smoke is happening together, okay? So we observe fire by our eyes, and the smoke detector detects smoke, okay? So fire causes the smoke, and then the smoke detector or the sensor detects the smoke, and then you hear some alarm, for example. So from observational data, imagine if we have some observational data, the probability of fire given smoke, okay, is greater than the probability of fire, had we observe that when we say that, the probability of fire, had we observe smoke, is higher than the probability of fire without smoke, right? Because the more we observe smoke, it could be fire, but it could not be also fire. But more likely from our reality, what we know is always when we see smoke, they are more likely, the probability of fire is higher than without smoke. Although we know that the smoke can also happen by some conditions, by some interventions. But sometimes, okay, let's change this one. And remember your conditional probability. The probability of smoke, given the fire, okay, if we are fire, when we observe fire, the probability of getting or seeing the smoke is higher than when we don't have fire. The probability of seeing a smoke without fire. This is from observational data. So observing one increase the probability of the others. Okay, observing either of the fire or smoke increase the probability of the other. Therefore, we could say fire is statistically is dependent, not independent, is dependent, are highly correlated between the two phenomena. But the problem is observation is not enough. We cannot say, can fire, if we make fire, we could get smoke, or if we, for example, like for the first one, if we intervene, or if we generate smoke, does it mean that we necessarily get a fire? No. How? Let's look at this example. Why observation is not enough to determine causality? Why? In this example, why do we know how do we know the fire causes smoke? Or what do we mean that? When we make a fire, when we make means, remember, the word make is about do. When we make a fire, we are likely to see smoke. Assumption we have is, like, let's say that the fire is in nature. If we do smoke, sometimes without fire, without making fire. For example, we may create some smoke by releasing some gas capsule from the sensor. Okay? But we shouldn't really expect the fire. So we need to intervene via experiment, which is to force a variable to a certain value and observe the change in the outcome variable. Therefore, intervention is necessary here to understand causality. Therefore, it determines causation. So let's do. So in this do operation, remember, I deliberately bring this analogy. But remember, when you want to intervene on some of the phenomena in your world, in our community, or in clinical setup, and etc., our intervention may be perfect. That means we perfectly said that intervention is, for example, fire is the perfect intervention to get to get the smoke. But sometimes we may create some imperfect intervention. Rather than inducing fire, we may like reduce and we may design some imperfect intervention, like something that may affect fire, like reducing temperature, so that we don't get smoke. That's called imperfect. But under ideal condition or an ideal intervention, when we set a variable when we intervene, the probability of y, or the outcome, given that variable that we intervene, is similar to the probability of y without intervening, because we believe that this is a perfect intervention. This is the only reason that caused the fire. Let's perform do operator here. When at some point, at some areas, we need to produce or we omit smoke. Our intervention would be production or omission, okay? To observe a fire. We produce or omit fire and observe the smoke variable. Let's do smoke. we create smoke, such that simply we are saying that when we do smoke, can be produced this, but we may not get fire. But when there is no smoke, smoke is false. When do is false, or with this notation, yeah, that means we are preventing smoke by example suction, okay? Or we may induce fire by ignition, striking the match, or we may not induce a fire. We should prevent the fire. That is the way we intervene. So let's intervene on smoke and see what happened to the fire. When we intervene on smoke, like when we do smoking and try to get fire, the probability of getting the fire without smoke is almost equal. Therefore, we would assume or we would conclude that smoking is not the cause of the fire. Remember our observational conclusion that we said the probability of fire as we see smoke is greater than the probability of fire without smoke. It could be greater than, but it doesn't mean that smoke is the main cause of the fire. Let's do fire instead of smoke. When we intervene on fire, like when we ignite the fire, the likelihood of the probability of getting smoke is higher without having the fire. Therefore, we can conclude that, by extension, we can conclude that fire is the cause of smoke. So this do is similar to our previous conclusion that we have in our previous slide, that we say the probability of smoke, we observe, not doing, we observe or we see fire is higher than the probability of smoke. Therefore, this implies that from observational data, whether we intervene or not, we would get the same estimate as, well, the same probability distribution of the smoke, whether we induce, whether we ignite the fire or not. That is the basic principles behind the idea of getting or answering our query or answering our question without intervention. Like just by looking at, from observational data, there could be the possibility to get or to get the true estimate of that. To do that, just this is what I have explained in the first slide about when we have a perfect randomized trial, we would get the same probability distribution whether we intervene or whether we observe. Okay, unless we have, we create without knowing or with deliberately, we ignore the value of H. Okay, but if we assume that we don't have unmeasured confound or unmeasured confounders or hidden common cause, we can assume that the probability, whether we intervene or whether this is the probability of observation, this is the probability of intervention, therefore we would get the same estimates. So to manipulate this, we may go through some rules, either through insertion or deletion of some observations, like remembering our graph. We have set of graph. For example, this is a graph. So our intention is to estimate the effect of X on Y. So we said if we intervene X, that means if we set X into certain value, that means we agreed that that implies that all incoming H to X would be removed. That means incoming H to X is removed in this X bar. Okay? Therefore, we could assume that the probability of Y having or observing Y, given we have Z and the W is equivalent to the probability of or only the probability of Y given W. by assumption, when we if and only if y is independent of z given w. Therefore, the only variable, like in our DAG, we should really adjust for it only w. Therefore, removing z or deleting z will not really change our interpretation. We would definitely get the same estimate, like whether we observe z or not, whether we put our z in our model or not. If y is independent of z, we would definitely get the same estimate as if we only just adjust for only w. Okay. Therefore, this probability is almost equivalent. Let's take this example that I got from this guy. Imagine you have a causal query or an intervention. You want to estimate the probability of difficulty in breathing. You intervene on cough, given mediator. Okay? So now the question is, should we include mask? This is our graph. Like, this graph is an exemplary graph that for COVID, that prior to we know what's happening on COVID, there's some issue about whether mask can reduce or not, whether social distance can reduce or not. But this is, in general, what I want to say is this is a causal graph, that is a DAG, okay? There is some season, there is some mask, there is some social distance. This both affect COVID, magnitude of COVID, and then having a COVID has some congestion, some fever, some cough, some difficulty breathing, and difficulty breathing let you to admit to some hospital, and then you need some ventilation, or having that cough or fever you may or you may not take drug. Okay, you have cough, you may take drug. You have fever, you may take drug. But so drug is a collider here. But in general, if the causal query, the question is for you is, what would be the probability of difficulty of breathing? How do we intervene on COVID? Like, how do we let someone to acquire COVID or not? What is that probability given we have mask? Like we said, we agreed that when we intervene on set of variable, or when we do some variable, we should really remove all incoming arrows or incoming edges. Therefore, that means there is no variables that affect COVID. We remove social distance. We don't need them. So the probability of intervening on COVID or letting someone to get infected or not. So the probability of difficulty breathing depends on the way whether we let someone to acquire COVID or not is equivalent or the same as the probability of having this COVID without adjusting F. So we can delete or remove this variable when we model. I think if you use DAC or R, they can easily just show you without understanding this phenomena. That's why I brought it. But if you draw this graph on your DAGITI or using R, it definitely tells you for which variable you should really adjust. It tells you that, adjusting for mask doesn't add value. So you can remove mask. Okay? Intervening on mask or observing mask doesn't add any value to understand the estimates of difficulty of breathing we intervene COVID. That's called rule number 1, or insertion or deletion. The second is about sometimes, instead of just removing or deleting some observation, we may exchange intervention and observation. We check the relationship between that variable by exchanging those actions and observations. That means the probability of Y, imagine we have two set of variables that we are going to intervene, do X and do Z, given W is equivalent to the probability of only just doing on only X is enough, and we could only observe without doing. Okay, we change this doing that action to observational, because the assumption we have is Y is because Y is independent of Z. Had we really intervene on Z, and that is doing X, and we also observe Y. So G X bar is all incoming edges or all incoming arrows from to X is already mutilated or cut, and all outgoing X to Y, outgoing Z and underscore bar is the sign of that all outgoing edge is removed. Therefore, the probability of, we don't really invest a lot of our effort by doing two interventions, like do X, do Z, and given set of variable. When we get by doing only one intervention and just simply observing Z would be enough. Okay, that gives us some true estimate, similar estimate as intervention. Example. Suppose if you want to know the probability of ventilation had you intervene on mask. Imagine if the government wants to promote mask use, what is the probability that intervention would reduce ventilation or someone admitted and receiving that what is this ventilation during the treatment, had the government really introduced such policies? That's the question where this rule 2 would help us, like exchanging both. So first is we have to understand, when we look at this graph, we have to go and understand the paths between M and V. Okay, what is the pathway by which M could influence ventilation? Mask use could influence ventilation. Mask influence COVID. Okay, if COVID is reduced, less people are admitted and less people have difficulty of breathing. So, the pathway from M to V from this graph shows is always through causal path, causal direction. That means mask use or not use cause COVID, or reduce. If you promote mask, it reduces COVID. If COVID reduced, people who have difficulty of breathing would reduce. Those people, if they are reduced, more likely ventilation. We don't need ventilation. Okay, that is the direct causal direction from this graph. But sometimes could be more complex than this. But now the rule 2 is saying, how do we replace intervention? Rather than intervening, setting an individual mandatory policy. Let's make mask use as a mandatory. Whether we make it mandatory is intervention or not. Just simply let the people, remember Sweden, let the people use by their own, by themselves, of use of this mask. Should we really intervene on mask? Should really have mandatory policy on mask? Or should we just avail on the market and let's see that people can use that mask or not through observation rather than. So the probability of whether we do, or the probability of having ventilation, reduction of ventilation, whether we have a mandatory mask policy is similar, almost equivalent to without having that mandatory policy or without having that intervention, is similar. It doesn't change. Therefore, we can estimate the impact of mask use on reduction of mechanical ventilation in hospital by only just looking at cohort study or by looking at those longitudinal studies. We don't need to conduct this intervention RCT. We shouldn't really invest time and also money on RCTs. We can easily estimate the same estimate, can get the same estimate by using this rule. This is the one that really gives me a lot of headache about removing action. I better just to skip to let you read about this, because I have read a lot of things to understand this. That's the final rule about insertion or deletion of action. It is a complete set of rules. This for I should brought it, but I am not sure I really fully captured about inserting or deletion of the intervention. Okay, I will let you stop here and just read on how deleting or addition of the intervention can really give or similar estimate as observational study. Okay, with this, I will finish the basic ideas of causal inference. That is all about, that is, I would say that is an introduction part of the causal inference. I hope you will dive into more on this method and get like insights about this. Before I jump into this, how to estimate causation from observational data or estimating causal effect from observational data, I would like to pause and receive some of the question from you. Do we have any question? Joel, are you there? Joel? Okay. Okay, I think Joel is not here. Any question maybe from...
Yes, Prof.
Yeah, go ahead.
This is quite important presentation. Thank you for it. I just wanted to see if I can put depression, diabetes, to see if the cause effect can also come out clearly, and if we can also see some confounders and some other effects that can come in that are not directed to X and Y. Maybe you just highlight and see how that can be incorporated here.
Okay, can you repeat it again? Sorry.
What I'm asking is, for example, if I give you depression, diabetes.
Depression is the outcome or the X? Is it exposure?
Depression is the outcome.
The outcome, okay.
Yes, diabetes is the effect. So
okay. Outcome and the effect is the same. You are
outcome, sorry.
Yeah. So depression is your exposure, I think.
Yes, depression is my exposure. One is a cause, the other one is an effect.
Yeah.
So cause is depression. The effect is cause is diabetes.
Diabetes.
The effect is the effect is depression. If we have the two, can we mingle around those cause and effect and see if we can get some confounders there?
Yes.
And also some other letters that can try to be interfering the X and Y there.
Yeah.
How can we get, and which could they be?
Yeah, I got you. So the question is, what is the effect of having depression? Sorry, what is the effect of having diabetes on depression? If I correctly understand Marlo's question.
Yes.
What is the effect of having a diabetic on depression? Let's say X is diabetic and the Y is depression. So the first steps you have to do is about okay, you get this phenomena from your observation, from your hospital, from your reading, or from your advice, getting some like expertise knowledge. Okay. So what, and then you have to think about what variables could really influence both. What is the mechanisms naturally you expect why diabetic patient or diabetic individual would really get depression? Is it because they have common cause? That is it. Okay, let me go back to the three paths here. Is it because they have common cause? That is C. Or do they have some colliding factors? They don't relate, you know. Okay, first of all, where do you get this question? You get this question from your reality, from your experience. Like you have seen most diabetic patients are more likely to develop depression. So you will hypothesize that, okay, is diabetic responsible for the cause of depression? That's the question. Okay. In that case, you have to understand what factors contribute to both, that is diabetic and the depression, that is C. What path could be, what is the mechanism you expect or the causal path between depression, diabetic X and the mediator? What are those mediators and outcome would happen? Or probably, this diabetic patient and also having depression, maybe they have some collider. Okay. This is, okay. Let's say how do we explain collider? Let's example. Okay. Let's say hypertension. Okay. That means hypertension is diabetic patient are more likely to develop hypertension, and also depression patient depression can also may cause hypertension. Actually, the other way around, the truth. But for this example, let's say hypertension is the main colliding factor that really relate diabetic and depression. So to estimate the effect of diabetic on depression, first, you should, after you have this graph, that is where DAG would help you. After you have this graph, you should really think, like you should really sample, you should really account hypertension, because if you adjust for hypertension, it induces the relationship. So you may falsely say having a diabetes can cause depression. But if you assume that there are some confounding factors or confounders between the two variables, you should really adjust for it. That you should close the path that's called separation or closing the back door. Whenever you have any confounder who cause both diabetic, cause both depression, you should really adjust for it. Again, I would say maybe you have also some front door paths, like a path how diabetic first change into some conditions that's called mediator M, and then that's maybe the M is maybe the responsible reason why people are getting depression. So the first step is about, as I said in my introduction, always before rushing into the data, I said here, please, you have to really have some external knowledge about data generating the process. That means what reality, external knowledge do I really know from my literature, from experience, from reading, from expertise, that I know that diabetic can cause depression, so that you can estimate the causal effect of depression or diabetic on depression. But you need some data in addition to that. If your data is a single time point, like cross-section, or your data could be a longitudinal, two time point, and more than that. And then how do we estimate? Okay, in addition to what we have about DAG, So now I'm moving to how do we estimate the effect of diabetic on depression? That is one of the techniques called matching. I don't know if I get you and also respond to your question.
You really did, Prof. Thank you.
Any question? Any experience of estimating this causation or causal model? That you can also speak on your experience. Okay, no question. Okay, let me dive into this. How do we estimate cause and effect from observational data matching? Remember, the goal of every causal question is to estimate the effect of treatment or the effect of policy or the effect of intervention on the outcome of interest. Like, let's say our treatment is diabetic and the outcome is depression. The goal is to estimate the causal effect of diabetes on depression. The challenge in estimating this relationship is one, could be selection bias. Our population may be self-selected. Or maybe the relationship be due to some confounders. That confounder could be measured, that's observed, or could be unmeasured, unobserved. Or because of some measurement error, we may falsely associate the relationship. So how do we take into account those selection bias, confounding, measurement error, and get similar estimate as RCT? The ideal approach or the ideal design is called randomized control trial. However, two things would happen. One, the random assignment may not be practical. We may not really assign the treatment, like diabetic, randomly to someone. Like, it's difficult to really assign someone, to let someone to acquire, to have diabetic and see whether he developed depression or not. That's unethical. Or it's also practically challenging. How do you really let someone acquire diabetes? Okay. Beyond diabetic, behind there's some underlying factors that you should really take into account, like diet, or some not doing physical activity, or some cause of diabetes. So it's difficult even to assign sometimes. In this case, you really brought an interesting example. But sometimes, even if we do randomized control trial, we may not really randomly assign the individual. We may make some mistakes. But in some conditions, like quasi-experimental design, for example, the government just rush into some programs without randomization, like giving some of the interventions, like cash transfer is very common in Kenya, if you remember, or across Africa. Okay, for some, and it provides some counties and some cash, but some counties do not receive that cash intervention. That's not the random assignment. How did they select those households? Based on some characteristics. That's called observable variable. They select those households to provide cash. They select those households by some variables, like household poverty status, number of children they have, or agricultural production, land size they have. These are all observable characteristics that determine whether that household would be assigned to the program or not. Okay? In that case, it's difficult to manage, to conduct RCTs. Sometimes RCT is not feasible in terms of cost, ethics, practicality. Therefore, we rely on observational studies. When our treatment assignment is non-random, or it's based on some variable or characteristics, we would say that's observational studies or quasi-experiment. Therefore, we use some techniques. In the absence of this random assignment, if these two groups, when you look at these two groups, they would definitely differ with some characteristics. There could be some systematic difference in baseline characteristics between those who receive the intervention and those who do not. In this example, Marlow's example, there could be systematic difference among in baseline characteristics between those who have diabetic and those who do not have diabetic, so that we can compare their depression status at the end. Because diabetic individuals may have some special characteristics why they acquire diabetic as compared to those who do not have diabetes or who are not exposed to diabetes. Therefore, some of these things could happen because of confounder. Therefore, we may end up some confounding bias. Therefore, we need some propensity score, a tool to estimate the effect of intervention in an experimental setting. The propensity score matching is, it matches treated with non-treated based on the propensity score. We estimate or we compute the propensity score from a set of baseline characteristics, and we pair those household or those individual or who receive the treatment and the comparison group based on the propensity score. Okay? Propensity score also relies on the assumption that some of the observable characteristics untreated unit can be compared with the treated unit if the treatment is fully randomized. In reality, we cannot really observe these baseline characteristics. The bias could be from unobserved measure or unobserved data, unobserved characteristics. In that case, propensity score matching may provide a very poor estimate. The most strong assumption to use, even before you rush to use propensity score matching, you have to make sure that you have a set of observable characteristics that could be associated with both groups, that could influence both treated and control groups. But if you think the program could be affected by unobserved characteristics, it's better to not to use propensity score matching and go for another methods called, for example, difference in difference techniques. That's one of the methods that I really need you to read about is if the assignment to the intervention or treatment is based on unobserved measure, how do we take into account in our model? Okay, that is where the utility of difference in difference methods come in. So what is the intuition behind matching? What do we want to match? The intuition is about getting similar or comparing or getting similar population, whether they are in a treated group or in a control group. The assumption or the intuition behind matching is to have some similarity between those groups. It allows a constructing comparison group when the assignment to the treatment can be modeled on the basis of observable. It assumes unobservable is there is no unobservable, as I said. So let's take this exact matching as an example and consider how propensity score is very useful as compared to this exact matching. Imagine, let's look at this real-world example. The question is, consider a job training program that does not have a clear assignment rule. There is some program, some training program, there is no clear assignment rule, so everybody may come in and receive that training. And then, you don't have data on that, but the data on income, tax record, that contain both individuals that are enrolled in the program and do not, you have this data on income and tax. So you want to compare those who receive the training, those who do not training, on how their job training would change their income or tax record. So the first, just without any using propensity score, if you directly, exactly, you want to match these two groups, those who received treated or the treatment, who received the job training as compared to the untreated or control, you may just, for example, consider age, one variable. Okay, age 19. As exact matching, you have to get someone who is really age 19. Okay, let's add one more variable. Age is not enough. to determine the job training status. Age may not be even the main reason. Maybe it's gender. Okay, you have to find someone whose age is 19 and whose gender is 1. That means, for example, if the gender is female, is 1, age 19, female, you should find among this population, among the comparison group, who's really 19 and whose gender is 1 or female. Okay, maybe gender may not be enough to determine this training status. Okay, let's check the unemployment status. Okay, the months, how many, the question is about how many months you are unemployed, for example, for 3 months. Okay, from the population, we should really exactly find someone who is really similar characteristics, who is really 19, who is 1 or female, who has a job, unemployed, 3. Okay, and then the education, they don't have education. This is the exact match on this. Imagine the more we have, remember when we model, we do some OLS, we put a lot of variables like 10, 12, 15. How could we really comprehend like getting the exact match like this? This in reality is difficult, to be honest. We may get like the age is maybe perfectly fits, but the gender may be male instead of female. And it's even difficult for us to comprehend. And too many variables, too many X means too many covariates may have, may like create some complexities. They sometimes called the curse of dimensional. The more dimension we add, the more we get some complexities. That's called the curse of dimensionality. The data may be high, or or sometimes could also be low. I will discuss it later. So we cannot control for selection bias that arise when the assignment to the treatment is done on the basis of non-observable in this condition. We only observe 4 variables, but we don't know. So exact matching is not really appropriate. Okay, it's difficult if we have too many variables, because we cannot really easily get like 2 units having the same combination of those covariates. Imagine if you have, for example, a list of, let's say, 50 variables. If you are in genome example, you have a lot of variables. And imagine if we have an observation of 10,000, like DHS, they collect about 30,000, 16,000, 20,000. How can you really manage using this exact match? It is more complex. So we are opted to propensity score. So we compute the propensity score. Propensity score is the probability or the propensity to determine or to participate in that program. That's in our case, for example, to participate in treatment, to receive job training. We compute that propensity score just to facilitate matching. Okay, we match based on propensity, not on the covariate as the way we did this. We only compute propensity score and match those individuals within their values. So when we estimate propensity score, we have to remember 2 assumptions. 1, for each individual, for each unit, the distribution of observed covariate should be the same among treated and the control group. That means when we compute propensity score, the probability should range from 0 to 1. I said it is a probability. If we want to, for example, with Malu's example, if we want to compare the effect of exposure, that is instead of treatment, exposure to diabetic, given those baseline characters, given those covariates, for all individuals, when we compute the propensity of having diabetes, that is the first step of propensity score, is estimating the or computing the probability of having diabetes is the first step. And this covariate should be balanced in both groups. How do we get? The score should range between 0 and 1, and see the distribution, whether they are balanced or not, through graph and etc. I will show you. If the treatment assignment is also independent of outcome, Okay. If the treatment assignment, that means for us, for example, let's take depression, it's independent of diabetic given set of covariates. Then we can also say that it is independent of potential outcome, that the potential outcome that would happen after exposing it to diabetic, given the propensity score. Therefore, we could assume conditional independency is there. That means we have already considered all confounders, so conditional dependency would be satisfied or fulfilled. Okay. But at the assumption we have when we estimate the propensity score is the distribution of the variable or observed variable should be the same. So if two people, for example, have the same probability of receiving the treatment, like 0.5 are assigned available in treated or in a comparison group, and then we can assume that the treatment is random. Like we are trying to mimic RCT, randomized control trial, from the observational data. So to compute this or to use propensity score method, we pass through these following steps. First step is about understanding the data. It is where DAG, structural causal model, potential outcome, thinking from potential outcome framework helps you. You get the data, you define the treatment, you draw your graph, you select the covariate, you map your graph, and then you define the outcome. And then you see, okay, this is the model or representation I have. Now I will go to the second steps, start estimating the propensity score. How? You estimate the propensity or the probability of receiving that program or receiving that treatment using either logistic regression, probit, or some machine learning algorithm. I hope you remember you have received some of these supervised, unsupervised, ensemble methods of machine learning algorithms. So then you estimate, and then you use that propensity value or the probability value, and you take some of these methods, either of these methods, either radius matching, or you opted to kernel or nearest. What determines to choose is a distribution of this propensity score that we see in this step. Between this and this step would determine which methods should be used. Or you use stratification, covariate, or weighting. They all have both advantage and a disadvantage. And then you estimate the average treatment effect or the average among treated units. Okay. So step one, when you get the data, you must identify who is treated, who is not treated, which variables should be included and which variables should not be included. Okay. That variable should be the baseline variable, something which happened before diabetic, before the program. That should be baseline. Don't adjust. When you model your propensity score, please don't adjust for post-treatment variable. I said, after for example, the intervention is diabetic. After diabetic, you may see some of the, for example, anxiety, for example. Okay, people get anxious when they develop anxiety and they're diabetic on the first week or some months. Okay, this anxiety came after introduction of diabetic. So please don't put anxiety status on your model. At the same time, for the example I take for estimating the impact of training program, after training, you would expect someone would start having some knowledge about the subject, or attitude would change because of the training. We expect some. So don't put those attitude or knowledge status in your model when you estimate your propensity score. It should be baseline characteristics that should not be affected by the treatment or the intervention. Including too many variables or too few variables has its own limitation. too many variables may exacerbate lack of common support, or too few variables may may violate some unconfounded assumption. Okay, the conditional assumptions that I stated. So that sometimes they call it curse of dimensionality. The more variable, the more we get some complexities. So look, how could we really pass, or how could we really manage this curse? Okay, should we really remove, or what is the best way that we can manage complexities? That's where this machine learning comes from, or has some added value in propensity score matching. So when you select your variable or covariates, remember this DAG could be confounder, it could be instrumental, and again, confounder. It could be, risk factor. Why is the risk factor? It could be sometimes, when you want to estimate A on Y, you may have some I, that's a mediating factor, and you have risk factor, you have confounder, you have an instrument. You may also, your graph may also goes to such complexities, for example. Like this graph is showing you, like if you have a confounder, you have to adjust, the box shows that adjustment. Okay? You have to adjust for this. You have to, okay? Look, in this case, let me take this example in this A. The path between A and the Y is three paths. One, A can directly cause Y. Second, A can be caused by X, X can also Y. So because of X, A and the Y could be associated. That is backdoor. A can also be associated with Y through D, through C, through E, through Y. If you just closely look at C, C is a collider between E and the D. So if you open it without adjustment, if you open it, the path is closed, I said. Collider always close the path. But the mistake that we do is when we adjust for it. When we adjust for it, we falsely associate, there is some line, broken and hidden line, which associate D and E. Therefore, A, when we adjust for C, A cause D, cause E, cause Y. So we already open, we create some bias. Therefore, when you estimate propensity score matching, don't put those variables like instrument, collider, and the mediators into your model. The only variable you should really consider in estimating propensity score matching or score is confounder and the risk factor. It should also be something that happened prior to the treatment. So how do you, the second step of okay, you have already selected your covariates. Now you want to estimate. And that is the probability. So for example, that is diabetic is a function of, okay, logit. You put the outcome is the diabetic and the propensity score, and also it determines how the balance of covariate or you correctly specify your model. But also the propensity score method also dictates the estimation and the interpretation of your treatment effect. So when you choose the propensity score method, You have to be careful about the question you have in mind, whether the balance of a covariate, whether you have correctly specified or not, or what kind of causal quantity you are interested in. Is it average treatment effect, or is it average treatment effect among the treated? Because not every approach or every method will give you the same causal quantities. The first choice of the methods, or you can use propensity score, is using matching. You create a matched sample, those who have similar propensity among treated and control, and then you compare the difference in outcome between the two groups. That is matching. The second is you may stratify your group based on the propensity score. Stratification could be decile, could be quantile, or could be quartile. It depends on, the question you have in mind. You may stratify your group into the score of the propensity. Okay, you can say, okay, generate, instead of, for example, generate this group if they have propensity score less than 0.3. Let's change to, for example, a decile. If they have less than 0.3, would be group 1. 0.3 to 0.6, group 2. 0.6 and above, group 3. So you want to compare what happened, or what would happen receiving the intervention between these three groups, and then you see the difference. Or you may adjust that variable, only the propensity score, as a covariate. Okay, you adjust for the propensity for as a covariate. Just only putting that value. But sometimes you may see some people may add some additional covariates in the outcome model, because they may assume that this covariate also, or they may assume that this covariate also may affect the outcome. Also, they may assume that there's an observed measures that could influence the relationship. Or you may compute inverse probability treatment weight using that propensity score matching. So how do you assess the balance before determining these propensity score methods? You have at least 4 methods. You use matching, you compute, you go for stratification, you go for covariate adjustment, or you go for inverse probability treatment. But how do you assess the balance of the covariate? You have the set of covariate here, so you have to check, as in this example, for example, this group are those who receive the treatment as compared to the comparison. So you should really estimate, compute absolute standard difference. And remember, in table 1, every state is in table 1, published across our continent. They have this table 1. They start describing the baseline characteristics. But most of the time, they put p-values, the absolute standard difference. You know how p-values can be affected by sample size. P-value cannot really detect. For example, if p-value is not significant, it doesn't mean that the covariates are really balanced. The p-values can be influenced by extreme values and also the sample size. Therefore, in this, as a rule of thumb, we use the difference between the two after we match. The absolute standard difference is, if it is less than 10, we would consider that covariate as we can say that, these covariates are properly balanced.
Right, doctor?
Go ahead.
P-value is affected positively or negatively by the sample size.
Exactly.
I'm asking if the p-value, is it affected positively or negatively by the sample size? Or when is it affected negatively
Okay,
by
2
the
things for
sample
that.
size?
Exactly. Okay, I will explain. Imagine you have, and instead of absolute values, you have p-values. And imagine if you have a large sample size between these two groups. If the sample is large, you may not really easily easily get significant difference between the two. So p-value would be non-significant most of the time. It's difficult to, the more, remember the central limit here, the more sample size we have, because we expect similarity, the central limit here. When sample population approach to the population parameter, it's difficult to differentiate between the two. So p-value would be non-significant. Okay. But when the sample size is small, from the small sample size, we may easily get significant p-values between the two populations. And we may falsely say the two groups are different. Okay, it could be affected in both directions. When we have sample size, large sample size, we may not easily get the difference between the two. Or if we have small sample size, we may easily get a significant p-value between the two populations and falsely say there is a group difference. Did you get me?
I got you. Larger sample size is good. It is non-significant, but small one can.
Yeah, exactly. That is why one of the reasons when you really go to propensity score, especially for matching, you must have a large sample size. Having a large sample size benefits you because it's impossible to get similar characteristics, similar propensity within the population. Or when you get similar characteristics, you may drop some of the control so that you end up in a loss of sample. So having large sample size would give you a chance of getting similar characteristics or similar population. That is why they recommend for propensity score matching, large sample size is good to get the appropriate or proper control. So how do we assess, in addition to absolute standard difference? Sometimes we have to also look at this visual inspection. We have to use some quantile plots, a box plot, some box plot of this standardized difference, density plots or histogram, and see the difference. Where is the overlap? Look at this, for example, the first graph. This is the density of the score of opponent. The red line is the density of distribution. Imagine this X is the propensity score. This is the density. Y is the density or proportion of individuals who receive the treatment, for example. So if you look at the distribution, it looks like, the average propensity score lies around here, this broken line for that peak. So I would expect like more the peak, huge, like if you look at this line, more people have less propensity score. Despite there are some people, in this area, there are people who have some propensity score, but on average, when you look at the line, the propensity, the density start to decline. For example, if you look at around here, those population, despite they have the high propensity score, but the population is quite small. Small population will have a high propensity score. If you look at the blue line, if you just look at this graph, and then if you see, they have almost close to 1 propensity score. That is the probability of receiving the treatment. And then if you look at the density of the score of participation, the higher value lies around here. Maybe on average, according to this graph, on average, most population lies around this propensity score, like let's say 0.8. So the overlap between these two graphs are between these two lines. Only you will remove, if you are really going for matching, you remove those populations whose propensity score is less than, let's say this is 0.3, this is 0.8. Definitely you will remove this population who score less than 0.3. Again, you will remove some of the people who score between 0.8 and 1. Therefore, your sample size will be reduced. Therefore, you have to think, first, how large is this? When you look at the visual inspect this graph, how large is this width? Is it okay? Do I have enough sample to go and only look at the estimates among this sample? Okay, remember, you have collected about 10,000, for example, of population. And if, let's say, among the treated group, like 5,000, like 25% have less than 0.3. 25% of 5,000, you have already removed like close to I don't know, about 750 individuals from your data. And again, you will remove 25% out of this 750 individuals from your data. And from 10,000, you have already removed 1,500 individuals from your data set because they don't fall within this broken line. Okay, you have to think. Do you think this excluded individual have special characters? You have to separate your data and check whether they have special characteristics. If they have some special characteristics, they may induce bias. Okay, we don't know. I say there's some unobserved reason, unobserved variable that may let them not receive or not to receive the treatment. Therefore, you have to check those individuals and also check the sample size you have and determine which propensity score method really is appropriate to use. Is it matching? Is it stratification? Or should I really adjust for coverage? Or should I really go for inverse probability treatments? I said there are 4 methods. Okay. If you use matching, you'll definitely lose this 1,500. But if you use other methods, maybe it keeps your sample, but it may induce some bias. Okay, there is some trade-off between the choosing of this propensity score method. So you have to create some matching and check the distribution using histogram. That is the other way of looking at the data is through histogram and compare these two populations. And then you estimate, you choose the methods, especially the method I mentioned, you choose after you look at, and you estimate the causal quantity. Is it average treatment effect or average treatment effect? Okay, let's choose nearest neighborhood. What does it entail? The nearest neighborhood, like looking at your neighbors who have the same propensity score as like yours, is about getting the closest unit of comparison group, choosing as a partner. That is called the nearest neighbor. It could be with replacement. It could be done without replacement. If you do with replacement, it's about like you will have more control. One control can be assigned to multiple individuals. Okay, it increases the quality of your matching. It also lowers the bias, but it has high variance. That is, you have to think, do you want to reduce the bias and induce variance, or do you want to reduce variance or and induce bias? To whether to choose replacement, nearest neighborhood method with replacement or without replacement. When we say replacement without NNM without replacement, is about when we have one control for one each treated unit, when we have only one control. Okay. This is, for example, the pictorial diagram. Imagine this is individual who receives the intervention. The nearest neighborhood, the nearest neighbor, this individual has a propensity score 0.559. So who is the closest individual who has similar propensity score? So if you have to check someone nearest, goes to the left side and also to the right side, and check who would be the most appropriate. Between this 0.59, 0.52, we have 3 values. Between 0.59 and 0.57, we have 2 values. So this individual would be chosen for this individual as a comparison group. But sometimes with one individual may have like multiple neighborhood, as I said, if it is if you want to have multiple control, okay, it could be, you can also extend to this your neighborhood and see your comparison group and then estimate the average difference between the two. And instead of going for nearest neighborhood, you may also, it's difficult, absolutely getting or finding a very close individual. Rather than it's better to set some caliper, some distance. What is the maximum tolerable distance you would expect and you should take to get the comparison group? That is using caliper. You set some caliper or some distance or radius for matching. It improves quality, just to avoid losing of some individual. Usually calipers you can set up to 0.25. Most papers, sometimes they need to 0.1, but as a rule of thumb, you can set the caliper up to 0.5. So if you have this intervention, someone who received the intervention, and if the caliper method is setting, you set as 0.1, you would go to that radius below and above the one who received intervention by 0.1. And all population within this radius would be considered as a control for you. Or you may use kernel or localized linear matching method. What it does, the estimator uses, rather than finding individual matching of these 5 populations, why don't we take some average of those individuals? That is the assumption, that is the intuition behind local linear matching. Okay, it's just to reduce variance rather than taking all individual as a control. It's better to sum up and take the average value of individual. That is called localized matching. Then, okay, beyond this, you may also take that propensity score matching and use it as a covariate. Just you put that variable as a covariate. Okay, but adjusting for this covariate, putting this propensity as a covariate have some limitation. One, because the treatment model is model dependent. I mean, the treatment outcome, the propensity score is a model dependent. That means those characteristics that you assume in your model is a result, is from your design, also the data analysis you take. Okay, so it requires you to have really correct model specification. I really repeatedly mention about model specification. This is very critical. Unless you have correct model specification, your propensity score matching or propensity score may end up in some bias. What does it mean when we say correct specification? Imagine when you try to build your model, you assume some linearity. Okay, there's a linear relationship between the treatment and the baseline characteristics. But in reality, that's function. Linear function could be nonlinear or may follow some second order function called quadratic or cubic or some polynomial function. You don't know. Therefore, you forget about that relationship. Sometimes we forgot to put interaction of some of the covariates or baseline would interact. They may not necessarily cause by themselves, but when they interact with the other, they may have exacerbate the treatment. So when we put in our model, we may forget those interaction or functional form that may lead to model misspecification. Or you may also forget some very critical variable that also affect the model specification, and the model may be misspecified. The other way of handling this propensity score is using stratification. As I said, you may stratify your group into 13 groups by quantile, decile, or some strata, or based on some predetermined threshold. Okay, and then you estimate that the average treatment effect between treated and control. The final is about using that propensity score matching rather than going for matching and end up loss of balance, also loss of data. One of the latest approaches use of, why don't we inverse the probability of that score? The inverse of propensity score is most of the time we used, remember, in a survey weight, in a complex survey design, we use this weighting. So we want to create some pseudo population. like for all treated units, we want to estimate the one of the over the inverse of the probability of receiving the treatment. 1 over propensity score for the treated, 1 over 1 minus the propensity score for the control. That gives you some weight. Okay, some weight. But when you estimate that weight, your weight may be stabilized or not stabilized. You will see some of the things here. If you adjust for some covariates, it may create some instability. Okay, you need to take into account it depends on the correct model specification actually. But what is recommended is you should really stabilize your weight because of some extreme values or because of some covariate may end up in some instability. That means, imagine you have propensity score. When you create a CDO score, like let me say I have a propensity score of 0.2. When I inverse and I received the treatment among the treated. I received the treatment, my propensity score is 0.2. Let's say 0.8, I have already received the treatment. So I have high likelihood of receiving. So when I inverse 1 over 0.8, it will be equivalent to about 2 individuals. The weight for me is small, okay, because I inversed it. For the control unit, the weight would be higher, okay? If it depends on the propensity score you have actually. If the propensity score for the control is, for example, 0.2, maybe the inverse probability is 8. That means I represent about 8 individuals. That 2 individual is a pseudo population that assume a counterfactual world. That is, I'm saying that. Imagine I have received the treatment. When I inverse it, I'm saying that had I not received this treatment, what would have happened to my outcome? That is the what inverse probability treatment weight adds. But one of the limitations of inverse probability treatment weight is it doesn't take into account if for example, if you have only single time point, it only works for single time point. But naturally you may have some time varying treatment. Your treatment may vary through time. For example, let's look at this blood pressure and the treatment. Okay, someone has some systolic blood pressure and the diastolic blood pressure, and then they put it on some drug. Okay, that drug definitely would influence the blood pressure, it lowers or exacerbate, we don't know. But most likely we expect mechanism is it lowers the second blood pressure, the second measurement. And then the second measurement more likely determines the second drug, whether I should continue to receive the drug or not. And finally, I want to determine that the effect of that treatment on, let's say, the Y would be maybe kidney failure. Okay. So imagine the relationship between blood pressure and the treatment is really complex. One, the treatment varies. What I received, the treatment here could vary from here. There is some dynamism. I remember how this clinician works. They change the drug, they change the dose. Okay, they change the interval. It affects sometimes, and also this treatment could also influence the reason why I'm receiving the treatment. That's my blood pressure. Okay, the systolic blood pressure I recorded. I have during the baseline initial statement, for example, is 113. So the clinician, the doctor is rushed to force me to take some drug. And then after 2 weeks, I get some improvement because of the drug and lowers, and he ordered me, okay, can you reduce the dose? So the treatment here could vary from this one. My blood pressure here is because it lowers from 130 to, for example, to 90 or to 110. So both the treatment and the outcome varies through time. There is some dynamism. So how do you take into account those conditions just to estimate the causal effect of treatment and the outcome. In that, where is, okay, sorry. This is where the beauty of marginal structural model come in. Okay, it's a method of estimating our bias for this time varying covariates simultaneously for both confounders and intermediate. The interesting thing, look at between blood pressure 1 and the blood pressure 2, look at this treatment. It acts as an intermediate, right? But if you look at between blood pressure 1 and the treatment 1, treatment 0 is, look, it affects both blood pressures, the second blood pressure measurement, and also the second treatment. So this treatment is act as confounder. Look, can you imagine in the real world, one variable can act as both confounder and also intermediate at the same time? It adds more complexity to our relationship to get the causal estimate. So we need to have some novel ways of thinking how to handle this marginal structure model. So how do we do that? We use the same inverse probability treatment weight for each round, for each surveys, because this is a longitudinal. It's also time varying. So we estimate the probability, the propensity score, and then we estimate the inverse probability treatment weight, and then that would be used for our structural model. What does it mean? There are some steps that you should go. First, you should create your pseudo population using inverse probability treatment weight. That means you have to determine for each round, you have to determine the probability of receiving the treatment. Or you have to determine the weights for each individual for each round, because each round is affected by different conditions. There is some dynamism between those strategies. But remember, this is longitudinal studies. Okay? Imagine if a clinician is following some population like 100 hypertensive individuals for a year. Those individuals whose blood pressure was recorded during time 1, like in September, they may not be available during the time 2. They may die, they may lose to follow-up, or they may not come for this measurement. There are some reasons. Okay, therefore there's some censoring. Okay, there are some group who continue, there's some group who would stop. Therefore, we need to estimate the probability of those individual could be censored. So when we combine these two probabilities of censoring and exposure, and we use that as a final, that's a multiplication of these two, and then we put it in our outcome model that weight and estimate the marginal structural model and get the true estimate. Okay, this works for marginal. We focus on estimating the propensity score of receiving the treatment. We say receiving treatment. What if we model, rather than estimating the propensity score, what if we want to focus on focus on outcome model? We have outcome model Y, the treatment model is X, and the other is baseline characteristics. We used to speak, when we say propensity score matching, we used to just largely focus on estimating the treatment model. Okay, estimating the treatment. But what if we are interested to estimate, rather than treatment effect, if we are interested to estimate the outcome model, directly outcome, the Y? In that case, we will dive into these G methods. G methods, sometimes you may read as G formula, and also G estimation. It aims to estimate this causal effect, especially between the exposure, the outcome, and the confounder, especially over time, where we have a longitudinal. Okay, when the time varying, we have time varying treatment, but where we are interested in modeling the outcome model. So there are some techniques called G computation, G estimation. Inverse probabilities can also be one of the G methods, and the marginal structural models that I have discussed today. I hope you will explore. I wish you explore about this G computation and the G estimation methods. Okay. If G computation is focusing or G estimation technique is more on outcome model, and if inverse probability treatment is largely focusing on the treatment model, why, if to improve our model specification, why don't we combine both treatment model and outcome model? That is where the beauty of doubly robust estimation comes. It's a statistical method for this causal estimation to estimate when we have, while providing robustness against misspecification. You know, we may fail either in treatment model or in outcome model. When we say outcome model, is about the probability of predicting Y, that is the outcome. When we say treatment is the probability of treatment X. In both cases, we may misspecify our model rather than missing either of the two models. Like when we rely on G computation, we may misspecify. When we rely on inverse probability treatment way, we may specify. So why don't we combine both methods? The element of both propensity or inverse probability and also the regression, so that we can get estimate. Why? What is the motivation behind doubly robust estimation? Just to get some consistent estimate between of treatment effect when either of the propensity score or outcome model is correctly specified, just to get either of the two. Because we are really subject to misspecification. I said what makes misspecification is because we may put too many variables, causal dimensionality. We may forget functionality. When the relation should have been quadratic, we may just put it as linear. We forgot interaction. We don't have enough covariance so that we limit too few variables. We again end up in dimensional problem. So that may misspecify our model. In that case, the best approach of combining the two and either not to miss either of the treatment or outcome model is called doubly robust estimation. So how do we do? Practically, if you want to measure the effect of new medication on blood pressure as an example, adjusting for this example, age, gender, baseline blood pressure, you know how this doubly robust estimation help you? First, you estimate propensity score of the treatment, and then you regress the outcome. And then you combine the estimates of estimate using inverse probability or regression adjustment to obtain the doubly treatment effect of the estimates. You know, how do we do that? There are some ways, like can be categorized under this so-called, I hope you will read again also on this type of doubly robust estimation. Sometimes you may combine inverse probability treatment weight with regression adjustment, or you may, to improve that specification, you may augment, okay? Or you may choose targeted maximum likelihood estimation. You know, if we are really, our model is really complex, it's difficult to understand for us, we may go for these three methods. One of these methods is called targeted maximum likelihood estimation. Why I chose this? Okay, we use doubly robust estimation by its own, but what is the added value of targeted maximum likelihood estimation? This stimuli is also a doubly robust. It checks whether either the treatment or the outcome model is consistent or correctly specified, but it is a targeted learning. It utilizes a machine learning algorithm to construct your targeted intervention that adjust for confounding variables. Remember how this machine learning techniques works. So this stimuli combine our statistical approach with machine learning approach to improve the efficiency and the robustness of our estimation. Here is the roadmap. Remember, here is the systems that we want to understand. I know it may not be easy for you today, but when you repeatedly read again and again, you will definitely like this graph. But here is the thing. The true probability of knowing the true probability of effect of depression on, or effect of diabetic on depression sometimes lie somewhere here. Remember, this dot, the blue dot, is that the number of trials that we make to reach to that true probability. That is our parameter space. Okay, we want to get this P naught. We tried multiple times, and then we may get at some points when we repeat our survey, at some point we may get true estimate. Okay, but it's difficult to repeat our experiment again and again. So what is the nobility of machine learning, if you remember? So you have some set of data sets. They divide those data sets into certain segments, certain distribution or different segment, and check some cross-validation. And then for each population, for each segment, for each data set, you would compute or you will use some machine learning algorithm and then check the initial estimate or check the probability distribution of the data for each data set. Remember how the supervised learning support vector machine or those non-supervised methods are really working, including these ensemble methods. So the issue is, once we divide our data set into multiple points, multiple data sets, we compute a probability distribution for each data, and from that, we update our model and try to arrive or to reach to the true probability. That is the way that TIMLI is working. So what are the initial steps? Okay, you have to check your data. What outcome? You have to clearly define your outcome. You define your confounder. You define the treatment and get ready. And also pick which machine learning algorithm is really important for you. So TIMLI, what TIMLI does is it combines statistical approach with super learning or super learner, okay, with machine learning algorithm, like example lasso, random forest, as this is an example. You can check support vector machine or the other generalized boosting method and blah. There are a lot of approaches out there. You choose, combine with the statistical approach, divide your data sets, divide the data set, and estimate the probability distribution of your data, and then find some optimal or try to arrive or reach to this true probability, this final, what we were looking for. So there are some steps to do this maximum likelihood estimation. You will go through these steps, like, okay, you estimate your outcome first, estimate the outcome. To estimate this outcome, you may use G computation, for example. Okay, I said G computation is usually used for outcome modeling. So how do you estimate the outcome? Okay, you may use, for example, just GLM, generalized linear method using logits. Okay, or you may use some machine learning algorithm as an example. I said GPV, generalized boosting, whatever. So you add some, for example, this is another code. You have some of these super learner, and list some of these super learners, some of these libraries from super learner libraries that you download, like GVV or support vector or whatever you put, including generalized linear method, and see for each data set, it computes its initial estimate and it checks the initial estimate of the outcome for each data set. And the closest model will be chosen, the closest super learner, also the closest model will be chosen from this library that fits to your data. Rather than you rush into choosing logistic regression by your own, it's better the library you check your data and select your model for you. Could be lasso, it could be random forest, it could be this multivariate adaptive regression spline. Okay, when you estimate your outcome model, in this step, it goes through three scenarios. One, it checks had every observation received the treatment. That means had they also actually received the treatment, That means it computes the probability, the propensity score for all individuals. Okay? If every observation received the treatment, they actually received it. That is assumption. If we assume those who received the treatment assume they have already actually received it. Sometimes it's not the case. But sometimes the second scenario is when every observation received is the treatment that's set to 1. And then also you compete for every observation who are assigned to control. Okay, the expected value of Y given they are in the control group, given those covariates, the expected value of Y given the treatment, they received the treatment, given they received the treatment, and also given the covariates, and the average between the two, Q1 and Q0, is called G computation, the average treatment effect of G computation. And then in the second step, once you get this initial estimate for the outcome mechanism, it computes the exposure mechanism, your treatment model. That's the probability of receiving. This is the probability, the likelihood of getting the outcome. This is the outcome model. This is the treatment model. That means the probability of receiving the treatment will be modeled using using the techniques. Okay, and similarly, you pass through this similar scenario. Had they received the treatment? Had everybody not received the treatment? If the observation was treated, the inverse probability treatment, and if they were not treated, the negative inverse probability of not receiving the treatment. It's just why we do this, just to choose so this scenario, we choose the difference between the two, and choose some very important clever covariates. They call it clever covariates. Using these clever covariates, they estimate some influence curve or influencing factor. Okay, and then based on this second step, you go again update your initial estimate. The initial step 1 is the outcome model, this one. And then the third step, using that influential covariates, you again re-estimate the outcome and optimize this. The ultimate purpose is, there is always, when you do this inverse probability treatment, there is a bias and the variance, a trade-off. When you put too many variables, you may have high variance, less variance. Less bias. But when you put too few variables, you may end up in high variance, low variance, but you may end up in high bias. Yeah, to optimize that is the main reason where, just to reduce this bias variance trade-off, you go for the stimulus steps. And then finally, at the end, you estimate the average treatment effect between the two. Okay. This is my final topic. It is about target trial emulation. This whole topic that I really brought today is most of the time can be used in mental health data, whether you use propensity, inverse probability, stimuli, or this marginal structure model. They all can be used for mental health data, including this target emulation trial or target trial emulation. What the name implies? Okay, we said and we agreed that RCT could be expensive or unethical or impractical or untimely. So we rely on observational data. So we want to know what works. Okay, that's the question that we have, or what harms. What's maybe our question maybe is from negative, like example, in the case of pharmacology, we may just look at what is the effect of that some drug that we give for depression, how it is really effective, how it is safe. That's a question that we have in psychiatry. So we cannot really randomize and check and to see the effect of the drug, the safety of the drug, or effectiveness of the drug. What we have in our hand is We have already following these individuals, so we use that electronic health records from the hospital or from the clinic and interpret using this targeting trial emulation. The name implies we emulate or mimic the hypothetical randomized control trial from observational data. That is a clever way of thinking. How do we think our observational data act or appear as if they are randomized control trial? The target trial, the hypothetical trial, we assume the hypothetical trial, and we start emulating from observational data. Where is the data we have? Suppose some of you are maybe interested to apply for this call. You may go to the electronic health record or registries, or you may have some longitudinal or cohort studies or case control. So you can use this target trial approach and see the effect of certain drug, or see the effect of certain, for example, CBT or some community-based intervention on reducing the depression status or anxiety, whatever, psychosis. But you have to make sure that your data must contain all the necessary information to replicate. I said emulation is about replication or mimicking a component of your target trial. So the definition is a methodological framework we used in a clinical setting to design and analyze RCT using observational data. We are conceptualizing as an attempt to emulate hypothetical RCT. Okay, it's aimed to reduce bias, confounding, is typically common in observational studies. How do we go about it? It's simple. We use two-step algorithm. First, we ask causal question. That is pointing to the target. So we specify our protocol of the target, a protocol of RCT. For example, what is the effect of, let's say, one drug, RCT, or one drug that depressive or anxiety individual would take? Yes. Okay. Someone have a question or? Okay. Let's say, okay, the approach is just to reduce bias and confounding. One of the things why this target trial came is, one of the things we think when we think about observational study, we always focus on randomization because we don't randomize, therefore observational studies have some bias. That's not always the case. The source of confounding, the source of selection bias, or the source of information bias is not because they are not randomized. Okay? I will show you where potentially our observational data or cohort or case control data could be biased. So we specify the protocol, step one. What is the ideal randomized trial or pragmatic trial actually? We would design to answer our question that is specifying the protocol. And then we shoot the target. That is a pointing to the target, shoot the target. We imagine that hypothetical RCT that we would prefer to conduct. To shoot that, we have two options. One, to go to the world and conduct RCT as far as we have funding as some resource. Second, we use some data, observational data, and then emulate. That is the second step. This is some example of the studies that you might get interested. Like, imagine you want to test the effect of vaccination, okay, during pregnancy, during a time of COVID, when we have no idea about whether that vaccination would really affect the baby or the mother. We don't know. It's unethical to conduct RCT. But naturally, women start receiving the drug, the vaccine. Some of them receive the drug even without knowing they are pregnant. Okay? So there are some bias. So in order to improve our understanding whether that vaccination really has an impact during pregnancy, they design this targeted emulation trial. They just follow use observational electronic record of the pregnant woman and see and design the hypothetical RCT. So they specify the target trial and then they emulate, they mimic the same step in all steps and get the same true estimates. Similarly, for mental health, psychiatric conditions, there's some interesting studies that you can also explore or read more. What is the component of the ideal trial? Remember, after you conduct randomly assign, remember that two things. One, eligibility. Eligibility criteria is important in RCT. What is the treatment strategy? Who you receive treatment A, who receives treatment B? You have to clearly put in RCT. That is an ideal RCT. Now I'm designing ideal. What is the follow-up period? When should we start this follow-up period? This is very, very important. It is at the time of eligibility we define eligibility and assignment, or after some time. I will show you some bias. And then define the outcome. And then you compute that causal contrast of causal quantity of interest that we have. And we plan our analysis. Okay? This is the step one. You specify the ideal hypothetical RCTs. You repeatedly sit and repeatedly do the same approach for observational data. Okay, you have an observational data. You have to define similar definition that you gave for this hypothetical. You give the same definition for eligibility, treatment strategy, and start of follow-up, outcome, causal contrast, analysis. You put the same. Okay, that is steps. Okay, this is some of example why observational studies. For example, in the studies on postmenopausal and heart disease, how hormone affect heart disease. If you look at observational studies, most observational studies, including systematic reviews, showed in this journal, hormone therapy would reduce heart attack by 30%. But if you look at the randomized control trial, only randomized control trial, even the studies show that this hormone induce, it affects the heart than protecting. So these two findings are really contradicting. So where did this mistake or where did the challenge lies? Why these two, either observational study give different meaning or different finding or result as compared to the RCTs? The problem is the way they define the eligibility criteria. When we compare observational study, we always compare those who are already currently using and with non-users. That is one of the mistakes that we do. But these current users are maybe depleted of susceptibility. There's depletion of susceptibles in the current users. I will show you one. And then when the RCT, when you look at the literature from RCT, they usually start from, after they assign individuals, they start following from new users after they start initiating, and they follow for some time. And then when you look at this post-menopausal therapy, hormonal therapy has an effect. So what happened in RCT? What is the ideal RCT? Usually three things will align when we do RCT. When we do randomization, three things always align. One, eligibility criteria. Once an individual have fulfilled eligibility criteria and assigned to treatment, you must start the follow-up. That is the ideal RCT. That is whether it is pragmatic or normal efficacy trial. Once you define eligibility criteria and assignment, you should really start follow-up of your treatment strategy, whether they are assigned to this treatment or assigned to the control or this treatment. But what happens if we start following up after treatment was initiated? one of the mistakes that we do in observation because of the nature or because of the data collection. The treatment was already initiated. Example, the NGO has already conducted for some treatment and avoid prevented not to give for the other. And you came after 2 years, you start following these individuals. You know, if you look at, imagine if the treatment is very useful, it's very protective. Those who do not receive that intervention are more likely to die before you start following up. The intervention has already occurred. You did not follow up to 2 years, for example. But when you come and start comparing these two populations, this population who did not receive the intervention might likely to die. Imagine this is in a clinical setting. Therefore, the susceptible individual will deplete. So comparing this group with those who have already reduced or less susceptible to group is creating some mistake. We're creating some mistake. It's difficult to compare these two groups because those who have received the treatment are more likely to continue, be healthy as compared to this one. Imagine if the treatment is harmful. What you give are more harmful if it happens. When you start following up, those who have already exposed to that treatment are more likely to die because it's harmful. So the population is reduced, so the depletion of susceptible. Okay, they are reduced. Okay, so if we start following up after treatment initiation, we may end up in depletion of susceptible. That causes some bias. Difficult to compare these two populations when we start following. What happens if we start the follow-up before the treatment? Sometimes, look, we start the follow-up because of the diagnosis, like HPV. Most of the time, we diagnose some people like cancer or human papillomavirus, or example, depression. But the treatment initiation may start after some time, like after 2 years, after we assign them. We have assigned this individual to the treated group and this individual to untreated or control group, but they did not receive the intervention at the time they should have received the intervention. They start initiation after some time. It could happen in reality in observational studies. During this time, this individual have an immortal time bias. There's a concept called in this model, there's an issue that we should really be careful about, is called immortal time bias. Immortal time bias is the time between after you start following up, when the treated individual, those who are assigned to treated individual do not receive intervention, are more likely, actually they are more likely to die. But we assume that we have already assumed that they receive that treatment, so they become immortal. So we falsely include or exclude some of the group from the analysis. So to avoid that, we have to be careful about the time of the introduction, the time where the follow-up started. Does the eligibility criteria came before assignment, and then the follow-up came after that? Okay, what kind of selection would occur? You would get this. If that follow-up came at the time of eligibility, but the assignment or the treatment has already, and they have already started, you end up in this selection bias. Sometimes the treatment occur, the follow-up occur before the eligibility and the assignment. That is where we end up in time immortal bias. In these two conditions, we call them susception of depletion and susceptibles, depletion of susceptibles. Okay. So if this is an exercise, imagine we want to emulate the effect of cognitive therapy on depression outcome. How should define, if we are going to do some hypothetical RCT, you have to clearly put your specify your targeted trail, and you emulate, you identify the data and then you emulate. That is the steps. and put it. Okay, this is all. I know that I have brought a lot of things just to motivate you to join this field. Let me have your question in the comments. And with this, I will close my session. So over to you. I don't know if Joel is here.
Hey, hello.
Yes, go ahead.
Yes, just before you close, thanks so much. This is quite interesting and informative. Do you have I wish you could shed some light on deep end-to-end causal inference?
I mean, my material, you mean?
Do you have any material on that deep
Yeah,
end-to-end?
exactly. Yeah.
Especially if you can have some template or some script in Python, which I can try to customize because I'm working on something and I'm really struggling to work
Okay.
out that code. Yeah. Or you can
Okay.
touch base offline if you have time.
Yeah, I can send you the Python code, some generic
Yeah.
Python code for some of the method for matching, for or what inverse probability,
I
for
mean the one for deep
stimuli.
end-to-end. The DESI is called DESI, deep end-to-end causal inference.
Okay, I didn't know that subject. I'm sorry. I confused with, yeah.
Maybe
I
that
can also
I
check.
can't.
Yeah. Is it from, maybe this kind of language came from field of machine learning. I don't know. I haven't read end-to-end causal inference. Okay, interesting. Okay, I will check, and can you send me an email? I will read and I get back to you. And then put my yeah. Yeah. Please send me this. I will get, yeah, thank you.
Yes, I've dropped my email as well in the chat.
Okay, thank you.
So once you're ready, you can have offline chat.
Yes.
Okay, thanks.
Any question? Yeah, today is quite yeah,
Then
today is not
the last one you did, this targeted trial.
simulation trial.
Yes, how is it different from use of synthetic data to do the same thing?
From synthetic data?
Mm.
Yeah, no, no, this is not yeah, we have already real data. I'm saying we call it real world data. We do not collect it for the sake of research, but we have some real world data in hospital, for example, electronic health record, medical health record, and there are some data that the government capture, like registry. So we are trying to utilize that data, mimic as if it is this randomized trial, okay, and then try to estimate the average treatment effect. So synthetic data is, I think, the data that you create for simulation. I don't know, probably one of the reasons. Yeah, but in this case, we have already the real data, observational real data. Okay. Computer. Okay, I will do. Okay. Any question? Or you can also raise some. I know most of them already dropped. I want to hear because we have been through this capacity building program for like almost 5 months. I hope some of you have already joined most of the sessions. I want to know, what do you learn? What went right? What went wrong? How can we improve? And it was like your time, energy, Does it motivate you? Whatever. Or is it waste of time? Any reflection, if anybody can talk on that.
Excuse me,
Yes, go ahead.
I have a question different from that. My question is about propensity score method. You said something like for us to get the correct method or effective method, there's a need for balancing scores, in which you are trying to say that probability distribution of observed covariates should ensure that they are the same for treated and control groups. So my concern is that in many cases, we tend to get observations which are non-parametric. They are distribution free. So I don't know how you can go around this, ensuring that the distribution of these observations are the same, given that in the first place they are not difficult. They are difficult to be ascertained, to have maybe normal distribution or any other type of distribution. How do you go about that situation?
Yeah, it's very, very interesting question. The idea why we go to matching, like why don't we directly go to oilless, is like regression. Regression is more restrictive. We know we deliberately blind to those assumptions of regression. And we rush to this, whatever we do, linear or logistic regression, and get our estimates, right? But if you look at some of these assumptions behind this regression, is really, they are restrictive. So the reason why we move to this distribution-free or non-parametric approach like this propensity is because we are looking for some less restrictive non-parametric distribution or non-parametric approach. So when you look at the balance, as you said, it could happen, some violation, as you said, yeah, we may not really get a normal distribution. Even there is an assumption called positivity, where we said the probability of receiving the treatment should lie between 0 and 1. Man, someone should have, given that covariance, someone would have some certain value, certain propensity score. But in reality, when you compete, you will get in some of the condition, like you will get definitely 1 propensity, or you may get 0. Given you have set of covariates, you may get some 0 probability, while we are expecting the score should be between that. That is where it violates. Yeah. So that would be the main reason why we should be careful about the propensity score methods we choose. Depends on the balance or depends on the distribution of these propensities. Depends on the research question we have, and it depends on the causal quantity that we are interested in. Imagine if we are computing average treatment effect, and we are going for matching with significant loss of data, and we opted, for example, we choose nearest neighborhood, and with loss of data, we may not really get average treatment effect. What we did was average treatment effect among the treated. So it affects the generalizability of our finding. We cannot really generalize our finding from the nearest neighborhood estimate or from kernel or whatever radius estimate, because they always tend to compute average treatment effect among the treated. Because we have already reduced the sample, we have already reduced the population. Then, okay, if our causal question is about quantity of interest is ATE, I would prefer to go to inverse probability because it keeps at least all population, the whole sample population. So checking the balance would help you to guide, okay, do I have a lot of overlaps? Okay, shall I go to a matching or stratification or covariate? Or should I really choose inverse probability treatment weight? Imagine if I have like a very small population of overlaps, really. Looking at that graph and going to the nearest neighborhood with this small width of overlap is really a kind of shooting our surface. It's impossible even to estimate. That's why most people who publish propensity score marking should really show the correct balance. And they should really show either using graph or using standard mean difference. Yeah. Over to you. Maybe if you have any experience, you can also share with the team. That is what I can say.
Thank you for your response.
Okay. Okay. Any comment on the program? No? Okay. Thank you, Dungo. Okay. So I wish you good luck. If you are going to submit, we have, I don't know, you know this, we have already opened the call for submission. Please just focus, team up, yeah, strike your target, and then I hope you will win and we will meet in the next chapter of capacity building. I wish you good luck. If you have any question, you can still forward to the project email or to me. Yeah. Have a good evening and good day.
Your email, please.
Okay, my email is
Can write on the chat
yes.
kindly.
Yeah, put it. Okay, with this, let's close our session. Thank you very much. Have a good evening. Bye-bye.